Hello everyone, this is Chomgasa Joven and I'm going to be presenting to you my paper reviewing which we carried out last week. So basically the paper that I was reviewing was, you can see the title there, it is Predictive Analysis as a Service for Vehicle Health Monitoring using Edge Computing and AKNN algorithms. So I'm going to look at those two main keywords, which are edge computing and AKNN algorithms. And those there are my keywords, as you can see. So let's dive in straight away. So the application domain of the paper was mainly within the industry of 4.0. So there was concept of just utilizing machine learning algorithms to detect component failures in vehicles. So this problem always arises in vehicles, and the paper was all about coming up with solutions to this problem. So the use of edge computing is proposed in this paper to monitor vehicle health that predicts risk of each of the vehicle components before actually the risk happens. So this is the basics of edge computing. Because edge computing, we know it's the paradigm where data is processed closer to the source of the data generation. So here where the vehicle is moving, closer to the vehicle, that's where data is processed before it goes to the cloud. Basically, that is edge computing. So this is another explanation of how edge computing occurs, whereby we have sensor data from the immediate point where data is collected, then edge computing occurs, then later on, that's when they transform the data to the cloud, where it is pre-processed, but edge computing happens before the data is sent to the cloud. So these are some of the devices that are used to get data from the vehicle, which we have one device is called scanner tool and OBD2, which are used for vehicle diagnosis. Then this is the computational problem that the guys were mainly focused on. The computational problem addressed in this paper focuses on utilizing vehicle health monitoring in smart logistics within the industry 4.0. That is the era in which we are currently in. So the proposed solution was, instead of sending vehicles to service based on time of vehicle condition, an intelligence system based on edge computing is proposed. So they have proposed an intelligent system based on edge computing instead of just predicting by themselves that the car needs service depending on its time or the condition in which it is in. So this is the way the system will look like. You can see here they are getting data from the vehicle. They're getting data from the vehicle here using this OBD port and OBD2. Then they send the data to Azure. Then it, through the Internet of Things, that is Wi-Fi, data is the predicted solution or the conclusion is sent to the driver through his mobile device or laptop, phone, or even the dashboard, and they can tell the driver that the car has a problem or not. So this is also another working of the predictive diagnosis, whereby they are going to be monitoring the vehicle health. Then they gather information, they transmit the information, then they analyze the information, they analyze and validate the information, then they forecast the maintenance of that particular information, then they send information to the driver to tell him whether to organize to visit a workshop or not. So this is how the app will look like. You can log in, then you select the sensors, then they predict, then they tell you whether the vehicle is in normal state or whether the vehicle is not normal and it needs to be worked on. So the machine learning models that were used, it was a combination of KNN and ANN. KNN is K nearest neighbor and ANN is artificial neural networks. So they combined these two models to come up with AKN model, which improves the predictive performance of the model. So let me explain one model by one model after the other. So let's start with KNN. So KNN is the simplest supervised machine learning algorithm mostly used for classification, where it classifies data points based on how its neighbors are classified. So KNN depends on its nearest neighbors and it predicts whether something falls in this class or in the other class. So this is basically what I mean. This is a cat, the black one is a data point, and it's put in this graph, and according to its nearest neighbor, you can see that most of its nearest neighbors are cats, and only one dog is near to it. So we can basically predict that image there, it's a cat, since all its neighbors, most of its neighbors are cats. So this is the KNN matrix. That's the precision, the recall accuracy, F1 score, NRMCE, and the loss. I'm going to go into details of this later. Let's continue. Then after after KNN, there was artificial neural networks. Artificial neural networks are computational models by the structure and functioning of biological neural networks in the human brain. And AAN consists of interconnected nodes or artificial neurons organized into layers. So in artificial neural networks, they predict depending on some specific layers. We have the input layer, that is the one where we enter data from. Then we have the hidden layers. Those are the layers that are used for classification. Then we have the output layer where we predict the output of the particular inputs that were inputted into the algorithms. So after combining the KNN and the ANN, they combined the two algorithms to come up with an ensemble model, which is known as AKNN. So let me explain this down in this diagram. So basically, they used leaf range market, that is LM, that's used for calculating weights. And then they trained the model using ANN. Then after training the model using ANN, the errors that were detected in ANN, that is artificial neural networks, were corrected by another model, which was KNN, that is K nearest neighbors. So after going through this process, they are able to come out with an ensemble model, which is known as AKNN. So this were the symbol, the way they assembled the model. They trained the ANN and validated on the sample data. Then the error reported from this base trained network is used by K nearest neighbor for statistical analysis of the errors that were there. So the evaluation metrics that were used basically in this paper, they used NRMSE. Then they also used code, accuracy, and ROC measures. So I'm going to explain each of these metrics in details. So let's start with NRMS. This is a measure of the accuracy of regression of a classification model. It is calculated as the square root of the mean square normalized by the range of the target variable. So NRMS is basically calculated using this equation that you can see there, and basically it's interpreted as allowing comparison across different data sets with verifying scales. So basically, the lower the NRMS value indicates better model performance. So the lower this value, the better the model. So this is one of the metrics that they use to evaluate this model. So as you can see there, you just get the square root of MSE, then you divide by the max of Y minus mean of Y. So another metric was cross entropy loss. So cross entropy loss is commonly used in classification, and it's used to measure the distance between predicted probabilities and actual class labels. So the formula is stated there, as you can see, and its interpretation is that low cross entropy loss values indicate better alignment between predicted probabilities and true class labels. So the lower this value, the more better alignment between the predicted probabilities. The probabilities that I'm talking about are the false positive, false negative, true negative, and true positive. So the code, this is the coefficient of determination, and this is the statistical measure of that represents the proportion of the variance in the dependent variable that is predictable from the independent values. So the formula of code is 1 over SCR and SST, where SCR is the sum of the square root, sum of the squared residues, and SST is the total sum of the squares. So code ranges from 0 to 1. So with high values indicating better fit, so the higher the code, the better the fit of the algorithm. So a code of 1 implies perfect fit, while low values suggest less exploratory power. So the higher the code, the more perfect the what? The model. So this code was also used as the valuation metrics. So these are the performances, as you can see, of the three models. As you can see, code of ANN and code of KNN and code of AKNN. You can see the code of AKN is quietly higher than all the others, and even NRMCE is lower compared to the others. So that implies that AKNN was better than all the other models. So accuracy was also another evaluation model that was used. This is a classification metric that measures proportion of correctly predicted instances out of the total instance. So its formula is true positive plus true negative divided by true positive plus true negative plus false positive plus false negative. So where TP is true positive, TN is true negative, as you can all see all those values. So accuracy is a straightforward metric, but it may not be suitable for imbalanced data sets. Higher accuracy does not guarantee good performance. So this implies that the lower the accuracy, the better the performance. So that's why they have said that higher accuracy does not guarantee good performance if data set has a skewed class distribution. So this is the accuracy of both of the three models. You can see this is the OB dataset. The OB dataset, we already talked about the OBD. You can see the precision, recall, accuracy, and F4F measure. And then the ROC, these are mainly graph curves that are used between true positive rate and false positive rate. So let me explain to them down here. These are definitions of true positive and true negatives. So these are the ROC curves. So you can basically, it's true positive rate plotted against false positive rate. So, and you can clearly see that the AKNN is the green curve, then KNN is the orange, and ANN is the blue one. So you can basically see that the AKNN was quietly higher, the true positive rate and the true negative rate. Hence, the AKNN was a better model compared to the other two. So besides here are some of the values that were corrected. Those are the false positive ones. And down there are the TPR and FPR. So these are the strengths and the weaknesses of the models that were used. So you can see that for KNN, high accuracy was achieved. Then its weakness is that sensitivity to irrelevant or redundant features. So it's more sensitive to irrelevant features. And even KNN does not work well with missing data or data that has a lot of noise. Then artificial neural networks, its strength was that they achieved 78% accuracy. And its weakness was it's prone to overfitting, especially with limited data. So if you have little data, that implies that artificial neural networks is prone to overfitting. Then the ensemble model, that is the combination of KNN and ANN. So its accuracy was 98%, which is a better percentage of the accuracy. And its weakness was that it is complexity in model interpretation. And there are potential challenges in training and tuning since it's a very complex model. So it's always a big problem while working with something that is complex. Then these are the strengths and weaknesses of the models and the evaluation metrics that were used. So as you can see there, the NRMS, you can see its strength, it reflects the relative accuracy of the model. Then its weakness is that it is sensitive to outliers. Then another one is code, which indicates the proportion of variability explained by the model. Then its weakness is that it can be misleading if not interpreted carefully. So if you don't interpret it carefully, your results can be misled by code. Then cross entropy loss, can also see its weakness and its strength there. And then the accuracy, which is it's an easy interpretable metric, but the problem is that it can also be misleading in imbalanced data. So data must be balanced enough for it not to mislead you. Then the ROC measures, these are basically the other curves that we saw. Effective in evaluating model performance across different thresholds, and its weakness is that it might not be suitable for highly imbalanced datasets. So conclusively, real-time forecasting of vehicle risk is an important learning from past errors, and it makes an adoption of the current scenario and predict future values with high accuracy. The proposed ensemble model AKNN is able to provide better accuracy when compared to ANN and KNN. So KNN, the combination of the two, was more suitable compared to when the other two models were independent. So that's why these guys came up with ensemble learning, which is combination of two models whereby the errors of one model corrected by the other model. So that's it. These are my references. That's it for today. We meet another time. Have a good day.